Okay, so we begin in 1 minute. All right. Shall we go, Felix?
Sure. So, shall I share my screen?
Yeah, I'll just give a brief introduction and then you can start with the talk. You could share your screen. Yeah.
All right. I think that's it. Yeah.
Great. Okay, so welcome everybody to this invited tutorial at LICS. Our speaker today is Brigitte Pientka. She's a full professor in the School of Computer Science at McGill University, where she leads the Computation and Logic group. She received her PhD from CMU, and prior to that, she studied at University of Edinburgh and Technical University of Darmstadt. Her research interests are on developing a theoretical and practical foundation for reliable and safe software systems. She received the Test of Time Award at PPDP 2018. We are very glad to have Brigitte give an invited tutorial today on contextual types. Brigitte.
Thank you so much. Thanks for the introduction, and also thanks to the organizers for inviting me. It's really a pleasure to talk about this work. Although it's now in a remote setting, I know it's been a lot of work for the organizers to get it into this format. So I really appreciate all the work that people had to put in moving the conference from Beijing to Saarbrücken and then moving it online. So the topic contextual types is something that has guided my research for quite a long time. It started actually in my PhD, during my PhD, while I was working with Frank Finning and also with Alexander Nanevsky, and culminated into a paper called Textual Model Type Theory in 2008. And then it has influenced a lot of the work I did after that. And so I thought I'll give a sort of an overview and try to explain these ideas fairly simply and where they play a role in various areas today. So before talking about contextual types, I think we need to talk a little bit about type systems and type theories to sort of see why we want something like contextual types to begin with. And so type theories, I think of type theories like Coq or ACTA, but even simpler forms, they really provide a foundational framework for describing mathematics or formal theories in general and establishing properties about them. And type systems play a very important role also in programming languages, where we just want to relate a program with the properties we can check about the program itself. And so the main judgment we usually look at is this relationship between a term M on the one side and its type A on the other. But we can also view it as M as a proof for proposition A based on this Curry-Hauer isomorphism. So the important thing when we think about this core judgment we're using in type systems and type theories is that it really describes a closed program. What counts as a proof is something that is closed in the end. And that seems like a very obvious observation. Obviously, a proof isn't a proof if it has some open subgoals. But the foundational framework really only checks complete proofs. And these are complete proofs that are closed. And that means it's a program that is closed. But while you are developing a proof, of course, it's not closed. While you're writing a program, it's not closed. It's partial. You do have, indeed, subgoals that are still open. And so what the goal is, in some sense, is to be able to characterize also the intermediate stages we might encounter in proofs and programs while we are doing this kind of program in proof development. So to make this a bit more precise, I want to introduce the simply type lambda calculus, which is the simplest form of a type system I can think of. And then we can sort of see how contextual types will arise and how we add them to the system and what power they actually give us. So the simpler type lambda calculus, we just have functions, function applications. I also added in numbers and variables, of course. And we have a base type nat, function space A arrow B. And then we also need to talk about type variables, because this judgment I gave between the term and the type is not quite accurate. As we go under a function, we encounter an m, which contains possibly the occurrence of this variable x, and we need to keep track of the assumption that x has a particular type, and that's what the context here is going to do for us. So the slight generalization of the judgment we've seen is really that a term m has type A in a context psi. And the rules are probably familiar with most of you. If you have a variable, it has type A if it is declared to be so in the context. You have an axiom. If you have a natural number successor of m, it has a natural number if m is a natural number. And here, most importantly, if it's a function, we extend our typing environment with the fact that x has type A. And applications just say m must be a function from A to B, and then n should match the input required. So if I give you a given program, right, like lam x, lam f, and applying f to successor of x, that is a complete program. It could be viewed as a proof for a proposition that says nat implies nat arrow nat implies nat. And we started out in this empty context, right? But of course, as we go along, it will not be empty anymore. And so in particular, if we are not yet sure what we should write here, okay, because we only may know when we start writing that this is a program which will take in some function and produce some natural number, we might want to characterize what is this thing that could be filled in, right, for this type. So, this notion of leaving holes in terms or propositions and types is quite common. It's not only when you want to do incremental proof development or incremental program development. You might think about unification, where you have holes in a given proposition or term or type that you want to fill via unification or via proof search or via program synthesis. But very often we want to have this notion of a hole. So, how could we describe this hole which is here inside this box, right? How could we describe this part? And it's not so obvious how we describe it, because it contains this variable x, which lives outside of this box. So whatever I plug in for this box, whatever term I plug in, it needs to have the right type, but also it can refer to this variable x. And whatever I plug in here, then this could contain the variable x in f. So if we look at this typing judgment, we have a context term and a type. If I type check this first part, the first box, then indeed, I have a term that lives in a context that has x in it, where x is declared to be a natural number. And so in order to characterize the type of this box, right, if I want to say, what is the type of this box now? I haven't written it just yet, right? I want to somehow fill this in via some kind of procedure, maybe by hand, maybe by some proof search, maybe by something. Okay. But I want to characterize a term that has this hole. Then I need to give it a type. And the type of this box is what we would call a contextual type. Okay. And it essentially internalizes this typing judgment we have, which talks about a term has a type in a given context, but it internalizes it as a proposition, or it reifies it as a proposition. So just the same way we have hypothetical reasoning that is internalized in the implication symbol when we talk about it in a proposition. Here we're internalizing this idea that we're reasoning by assumptions using this kind of contextual type. And whatever this contextual type describes is something that is in itself, in some sense, closed. It's closed with respect to this context we're given here, right? So what I plug in here is a term that can refer to x. So it is, in some sense, closed with respect to this local context x that I'm keeping track of. And here it's closed with respect to x and f, okay? So So that means we can now refer to holes. We could name them H, and we could give them a type, and we could list the types of these holes in a meta context, which is different from the local context I'm working with. And this is called the contextual type, and we instantiate it with what is called a contextual term. Okay, so in this case here, we wanted to instantiate it with f applied to successor of x, and it returns it contains x and f. So we keep that we keep them locally within the context we can access. Now you might say, okay, that sounds reasonable, but I might have chosen this variable name x and f to be precisely the variable name I have in my current local context. Okay, and there's nothing really that ensures that this must be the case. And so whatever we plug in for H in some sense contains these three variables, namely x and f. Okay, and now I seem to have crafted the scenario in such a special way that indeed, the variables I choose for the term I plug in, for this contextual term, coincide with the variables that are required from this outer context where I splice it in. And we really want the theory to be stable under alpha renaming. There's no reason why these bound variables should coincide. Okay? I mean, I can rename this x to y and this f to g, or I could rename here these variables x and y to y and g. And I would like the theory to still work, right? And so how we achieve this is by associating the contextual variable with a substitution that essentially does this renaming for us. Okay, so when you plug in a term g applied to successor of y in a context where you actually have x and f, we replace the x with the y, and the y with the x, and the g with the f. Okay, so it comes as a closure. So there are two important lessons to take away from this. One is that it's really important to separate the local context, which talks about the local assumptions I'm currently working with the global context, which in this case here contains holes. They are globally valid, they're true in every world. Okay? And that means, of course, I can also access them in my current local world. So now we have two contexts. That means also we have two kinds of assumptions. The variable x, which has type A, has type A if it is declared to be so in the local context. So if I am currently in my world where I have assumptions inside and I know x has type A, of course I can conclude that x has type A. But if I have a global assumption, right, in gamma, so that means essentially in every world it is true that I have an assumption that proves A from some assumptions in phi. Then I can use it in my present world as long as I can prove that I can satisfy all the requirements from phi. Okay, so essentially I can move from phi to my present local world psi. And in the previous example, this was just a renaming, the sigma, the substitution that was associated with this whole variable h. But in general, it can be really any substitution, right? That allows me to move from phi to psi. So it's not only a renaming, it could be an exchange, it could be a beaconing, and it could be, in fact, doing even a refinement, providing a concrete term for some of these assumptions I have in this context phi that are required. Okay, so this was going back, in fact, this idea of separating two contexts between a local context and a global context, that goes back to work started by Rowan Davies and Frank Fenning. They had a paper called The Judgmental Reconstruction of Modal Logic, where they gave a constructive view of the modal logic as four. And in particular, their interest was actually not in characterizing holes in terms. They were interested in code generation, where you want to separate the code that is generated, which then can be run in every world, and the program that does the generation. Okay, and so in some sense, the code that is generated is a closed piece of code, just the same way my whole is a closed piece of code, and it makes sense in every possible world. In their view, it can be run in every possible stage. And so in 2008, we generalized this idea of a box modality to a contextual box modality where we not requiring A to be closed, but A could refer to some assumptions here in gamma. So what they presented back in 2001 was a simply typed lambda calculus with this box modality, box A. And they gave two lambda calculi. One was lambda calculus with box and let box. So they actually have a way of introducing box and let box in the program, not only abstracting over it in the actual context, which I was working with. And they have an alternative formulation where they have box and unbox, which is more closer to sort of a Kripke style formulation of context stacks, where you have not only two contexts distinguishing between what is locally true and what is globally true, but rather you have a stack of contexts modeling the fact that a variable at stage I is bound in the context gamma I. And the unbox allows you to sort of access previous worlds in some sense. Okay. And the topmost context is in some sense your current world. So in 2008, we picked up this line of work and generalized into this open code. And what I wanted to draw the attention on here is that we presented also a simply typed lambda calculus with box and let box, where we distinguish these global and local assumptions. But we now characterize not only something which is necessarily true, absolutely, but it's true with respect to some assumptions gamma. Now, the 2008 paper also contains other things, but I really want to focus on this aspect. So, so what does this rule look like? Well, if you have a box construct you want to introduce for the box type, then we have, in fact, a context switch. So if M, which refers to some variables in phi, so this is this app, apply F to successor of X, for example, it has X locally still there, and F, then we switch the context, okay? We check that the code or the term M we have here is well typed with respect to phi. And we forget the previous local assumptions in psi. And when you were working with a closed box modality, this part here was empty. Okay. So the let box elimination form essentially says that if you can prove that M has the type box A with respect to phi, then we can extend our global context of assumptions with that assumption and continue to prove that N has type B. Okay, and that gives us a let form, a monadic let form for eliminating a box modality. So what can you do with that? Okay, why is this interesting to have, and why is it useful? Okay. But before that, I want to show you how they interact. Okay. So they interact through a local sameness derivation. So where we have essentially want to construct an introduction of a box and an elimination from a box. That gives us a redex in some sense where reduction would be triggered. And that means we have here this box form, box term M has type A in the context phi. That means M has type A in phi. And over here, we have extended our context with this global assumption U. And now we can do the reduction by eliminating the occurrence of U in N by replacing U with this open term M that refers to these variables still in phi. And I write phi hat for if it's just a list of variables. So there's a modal substitution property, or a global substitution property, if you like, which complements the local substitution property, which would replace variables here in psi. Right? This is your normal substitution property, which comes from the fact that you have implications in your logic or you have function spaces in your logic. But now, since we have two different contexts, we have two different variables, and there are two different substitution properties. And the important part is that if you plug in something for this closure occurrence of U with the substitution, you immediately apply the substitution to the term N. Okay, so there's no, so that's really we think of it as a splice, directly spliced in and the renaming is applied eagerly in order for the term to make, for example, sense. So, all right, so far I was talking about these contextual types as wholes and proofs in programs, but I was also alluding to the fact that that the original work was actually coming out of staged computation or meta-programming and code generation. And since it's much easier to make things more concrete in the setting, I also want to revisit this application of contextual types. So, so in multi-stage programming, it's really, the idea is that we're writing programs that produce other programs, okay? And ideally, we also would like to manipulate these other programs within the same language. And this is a very common theme, okay? So you find it in Lisp, Scheme, Template Haskell, MetaML, Template Coq, Coq and Coq, Template Acta, C, Java, Scala. Like you find it in almost any language out there. And the reason you find it is because it leads to, it can lead to quite some performance gains due to domain-specific optimizations you can do. So the most popular machine learning library implemented in C uses this idea. If you, in this application, you often have a matrix and you have a vector, but the matrix is often fixed, okay? And the vector is sort of what changes quite often. And so what you want to do is you want to, based on the shape of the matrix, so if it's a triangular matrix or it's a sparse matrix, you want to optimize what happens in the second stage when you apply the vector. And so this can lead to domain-specific optimizations that complement sort of what happens in the compiler. So that sounds great. But if you ever try to write a multi-stage program, it's actually not so trivial. It's really hard to test the code generation and the generated code in the end. And it's hard to reason about these code generation and the code generated in the end. And errors are often called at runtime when you run the generated code. And so that means it's very difficult to find the error in during the generation phase. So what makes it even more complicated is actually that in all these applications, there's a bit of a question how we should represent the code. And so there's this tension between untyped generated code and typed generated code. And this tension exists now regardless of what if your language is that is doing the generation is typed or untyped. Right? So certainly Lisp and Scheme, it's untyped. And when we say quote, give us the syntactic representation of a program, it's an AST, but it's essentially just an AST. It could be 2 plus true for all that matters, or 2 plus a string. It's just an expression, okay? And of course, you can do all kinds of things on it. You can pattern match on it, but there's sort of this key question on how do you handle open code? And how do you actually represent the code hygienically so that is well scoped? Now, there's other approaches in typed languages like MetaML or MetaOCaml, where you code an expression and you get an intrinsically typed AST, but you still have this question: how do you represent well-typed and well-scoped code? How do you compose code? Okay, and how do you support manipulation of such code? So via pattern matching. So when you take this view of box and let box, you to make this concrete, you would write a program, for example, for generating a code that extracts the end element of a vector. So a vector here is just a list of integers. And so I want to say I generate code that returns eventually an int given a vector. Okay, and so if n is 0 or less than 0, then I return a piece of code that says access the head of this vector. Okay, and if otherwise, I'm going to generate code for accessing the n-1 element of the vector. And then I want to splice it in. Okay, and I want to splice it in such that I replace this v with the tail of v, so that in the end I get here essentially head of tail of tail of tail of v, so n tails, to be able to access the nth element from that vector. So here I wrote with for this closure of the boxed variable together with the substitution, because it's a little easier to write in a concrete programming syntax. So here you see an example where the substitution we're associating with this open piece of code that is generated, like nth of 0 will generate head of v, which depends still on v. But we're actually instantiating this v with tail of v to bring it into the next recursive stage. So it's not just a renaming, it's not just a weakening, it is really a proper substitution. And I want to point out that there are many approaches in code generation and multi-stage programming, but none of them allow you to actually splice in code together with a substitution. They always require that the code you're splicing in lives in the same environment as the environment is required where you splice the code actually in. Okay, so so that limits in some sense the application domain. Now, very often we don't want box and let box, okay? Because for those of you who are familiar with this for scheme, there's usually something called quote and unquote, which is sort of a direct splice, okay? So quasi-quotation or quotation, the distinction is not really important. It's essentially saying, here I have an AST of a piece of code, 2 times x plus y, okay? And when I unquote or splice, I want to splice in the result of mult of 2 into this code fragment that still adds y. And now if I assume that mult of 2 generates code of 2 times x, okay, then I will get back 2 times x plus y after I splice in here the result of mult of 2. And now you might ask the same kind of question as I did before. Clearly I'm working here with open code fragments. How do I know that mult of 2 will generate something that contains x, so I can use it in this context, in this outer context, which has x and y? And what guarantees this in any form, right? I mean, I could have generated code that had this variable name a, for all that matters, and now I want to use it in a context where I have x. And so the answer is, again, well, we want it to be stable under alpha renaming, and that means we should really associate it with a substitution. We should have an unbox together with a substitution. So I want to point out, so if you rewrite this end function, okay, so here we have the let monadic form. We directly replace it with this unbox where we splice in the recursive call and its result directly. So this is already much closer to programming practice. Now I want to point out that all formulations I know of which attempt this extension of original work by Rowan and Frank in some form, they usually consider an unbox relation, box-unbox term calculus, but the unbox is always by itself, right? It doesn't come with a substitution. But it's very naturally motivated if one thinks of it as a contextual, that it does give you a lot of flexibility of thinking of it as a closed piece of code with respect to a list of variables that you're porting to a current world. Now you might say, why contextual types? Why not write functions? Okay, and that is a completely valid question. So you might see that this looks like a function in some sense. Okay, so why not actually write a function which is closed? Okay, why do I need something new? Okay. And logically, you don't need anything new. So it's not the case that we can prove more propositions with a contextual type than we were able to do before in Lambda box. It's same kind of propositions can be proven. It's proof theoretically equivalent. But the kinds of programs we can write is kind of different. So if you would write the end function with generating a closed function, you return here a function that takes in v and returns head of v. And then in the recursive call, r will be a function, which is then applied to tail of v. And the code you're generating for nth of 1 will be a nested function application. Okay. And so arguably, this code doesn't look like what you really wanted, right? You wanted to have head of tail of v. And that means here we have, in some sense, what is called an administrative redux, which really should have been eliminated at the time when we spliced in the code. because once we have code that looks like this, that gives actually hope that we can do code optimizations, right? We have an idea as a programmer, we have an idea of what the code looks like. And here the code looks like what we intended. While here the code does not look like quite what we intended. So we should not use functions for splice, okay? Because functions are in some sense far too powerful for what we want to do. Okay, so how can we describe, the type system for a system of box and unbox? And as I mentioned, well, in this case, we have a context stack corresponding to each of the worlds, where the variables at stage I corresponds to being declared in gamma I. And the local variables are on the top, okay, or in gamma n. That's my most current local context. And if I introduce a box, it means we push something new on the context stack. If you don't have a contextual box, then the gamma is just empty. It's a special case from a contextual type. But if it's a contextual box, it's where we have some assumptions gamma, we extend the context stack, we push something onto the context stack. And then the question is, how do we do unbox? Okay, the unbox is really the difficult one to deal with. So unbox pops context off the stack. We're going to a prior world, okay, and that means there are two accessibility relations we usually have in mind when we talk about S4. One is transitivity and one is reflexivity. And I want to consider them separately because they kind of do different things. So if we want to unbox a term, because M comes from a prior world, it makes sense in this prior world, N minus K. Okay? Then we want to port it to our current world, which is N. And the way we port it is normally by modal weakening, because now we have more assumptions. But in addition, we want to apply the substitution sigma to the local variables, which are here in gamma. So the reduction employs two forms, okay? Two forms of substitution, or one is more lifting or shifting, which comes from modal weakening, and the other one is the reduction of applying actually sigma to the free variables in this box N. So modal weakening says essentially that if you have access to N stages and you insert more, okay, that means just you have more hops. So this is like if you add some more transitive relations essentially in your accessibility relation. So modal weakening should definitely always hold. And that means here, you notice that M is required to make sense in the prior context, which goes only until N minus K. And we want to use it in this larger context. So we need to lift it. And the lifting essentially entails that any unbox constructs that appear in M need to be adjusted. These indices need to be adjusted. So the second part is in the accessibility relation. So that is K is equals 0. And in the code generation world, it's really like when you run code. You're not only generating code, but you're now executing it. Okay, you have generated the code for the end function, and now you're giving it a vector and you're running it. Okay? And here we also need to be a little bit careful because M makes sense in this context gamma 0 to gamma n, which is exactly the same context, the same world as when we do an unbox 0. But unbox 0 says we're staying within the same world, right? And so when we extend this context stack with gamma, with another stage, we want to really fuse gamma n and gamma together. So we're keeping the size of the stack in some sense the same. And so the simplest way to achieve this with the substitution is to have sigma be a substitution from gamma, but it's also, since gamma could refer to gamma n in general, it's mapping essentially the variable in gamma n to identical variables in gamma n. And so the reduction uses also a form of a structural property, which comes from the modalities, and it's called a fusion property, where we're essentially fusing the topmost contexts together. So, all right, so let's, I mean, I gave you a lot of technical content, so I wanted to also review a little bit what this has been used for. So I mentioned, you know, contextual types can characterize holes, and we have used it for giving a clean formulation of high order unification, for example. I've also showed you how one can use it maybe in code generation. And that really provides a different view of how we unbox code. But what have we used it for in the last 10 years? So the first application we've looked at actually was how we can use it for mechanizing meta theory. So how we can formalize and specify formal systems in the logical framework LF, which is here at the bottom of the iceberg. And then we write proofs about these specifications. So what we have up here is really a first order logic or an index type system. And instead of doing first order logic proofs about lists or natural numbers, you do proofs about derivation trees, which are defined down here. And the way to mediate between these two levels was done through a box modality. Okay, so here since these are derivations that would be open, or open terms, we are traversing them as we go along. They're not always closed. So we wanted to be able to describe these objects as being open. And this is a system that does have box and leg box in it. So it has a very explicit monadic style of writing programs and proofs. And you can extend it to handling induction and co-induction. And one thing you really need is essentially an abstraction of the context itself. So the context in all the examples I gave you was very concrete. But as you write recursive programs, you might not always have a concrete list of these variables. So you want to have the flexibility of actually abstracting over that list of free variables. So the second example I want to mention is Cocon. This was a paper we had at LICS last year and extended a Martin Löw type theory with this notion of contextual types. And it was again used to mediate between an LF representation, which has a weak function space. This is a function space where you want a pattern match on, and it's really abstract syntax it describes, and a strong function space, which is really what happens when you compute. Okay, and we mediate between these two sides again with a box modality. We can quote the code written in LF and then write programs about them on the right side. And we can also splice in programs directly when we're building these syntactic objects in LF. And they're really, you can think of them as ASTs with a notion of binding. And last, I want to mention a new project we've started, which is Möbius, which is started just about 8 months ago. And it is aimed at providing a novel foundation for polymorphic multi-stage metaprogramming. So here, as in the nth example, we want to characterize code that is generated. And we use box as a form of quotation and unbox as a form of splice. We have unbox together with the substitution, which gives us quite a bit more power and flexibility than existing approaches. And we can actually handle polymorphic code. So since we can have a joint context of term variables and type variables, we could write a function that, given a natural number, it applies a function f n times to x. Okay, and the way we would do this is if n is 0, it does not get applied at all. Okay, otherwise we are generating code. Okay, which would be, for example, if n is 0, it's just going to be x, and then we splice it in and apply the f to the spliced in actual code. And here, indeed, we splice it in with where the context, the generated code, coincides exactly with the code, the context where it is needed. So being able to actually characterize polymorphic code is quite unusual. Okay, so the work that has actually looked at polymorphism in multi-stage programming usually looks at it in the setting of MetaML and MetaOCaml, where we have a let style polymorphism. But here we wanted to think of it really as a sort of more system F style polymorphism. And there are a lot of interesting questions that come up from this point of view. But one of the advantages of having here a context is that we have dependencies now, of course, right? Here A declares a type variable, and that appears in the type of F. And so our framework is strong enough to express these kinds of dependencies and handle them in a safe way. And lastly, this gives rise to the idea that we can then also pattern match on code. And sorry, this brings sort of these ideas we had on pattern matching in Beluga or in Cocon to the multi-staged programming setting. Okay, so I want to also talk a bit about some related work, because there's quite a lot of active work on modal type theories. And so in particular, in recent years, there's some work started by Ranald Clouston, but also then continued with John Sterling, Daniel Gratzer, Lars Birkedal, and so on, where they have a modal type system where they call it Fitch style. You can think of it as a context stack, if you like. It's very close to the context stack formulation, except that they don't have the stack view, but instead of saying I add a new context, they have what's called a lock. They have a marker on the context. Okay, and then when they can unlock the context, which is sort of similar to our unbox, if you like. So, they have studied extensions to dependently typed systems. So for example, there was a paper at ICFP last year. But in this work, actually, they don't give really an operational semantics. They have an equational theory. But it's not true that all redices, actually, all well-typed redices would immediately reduce. And it only handles closed code. And further, the way it is described, it uses variables that are denoted with De Bruijn indices. So in that sense, yes, alpha renaming goes away because you drop down to a lower level and you forsake sort of the abstractions you have in the language. But this is certainly, there's a very close relationship, I think, which is worthwhile exploring more. I also want to point to some work some of you might have heard of. There's an extension of ACTA, which is called ACTA flat. There's also a CRISP type theory by Mike Schulman and Dan Licata, and this is work which comes mostly out of sort of the people who are interested in homotopy type theory. And there, they also have studied the S4 comonadic modality, like the necessity modality, and it's usually written as a flat modality. But in fact, it's the same rules as were present in Rowan and Frank's work. Okay, so I think they might not have been fully aware of that relationship, or might not have fully seen the similarity, but it's in fact it's the same. Now they're mostly interested in studying the category theoretic formatations. So you might think of Cocon or our work more as the syntax for such category theoretic foundations. They haven't really established any meta-theoretic properties about ACTA flat. So if you're using ACTA flat, you sort of believe that it is doing the right thing. And in order to maybe also to emphasize this close relationship, so over the last year, I've worked with Ulrich Schöp at the University of Munich, and we've looked at, again, the work by Martin Hoffmann on a semantic analysis of higher abstract syntax, where he presented a pre-sheaf model for characterizing Hoast representations. And we adapted that work to give a semantic representation of Cocon. And the way we did that was really, we actually reused this comonadic modality in ACTA flat to implement our model. Okay, so there's really a close relationship between these alternative approaches, although we all coming from it from different motivations or different angles. So I also want to briefly mention the trade-off. So I talked about box let box and box unbox, okay, but there's a clear theoretical trade-off between these two approaches. So box let box with two contexts, I find much easier to work with conceptually. It's clear, the operational semantics is very clear because it's staged in this way. You know exactly what gets executed when. You have these two substitution properties, modal and local substitution properties. So everything fits, it's beautiful, it's great. Okay. It scales to sort of index type systems, what we had in Beluga, very nice. But because you have box and let box, it's much harder to define normal forms. So anybody who has worked with normal forms in where you have lets, you have to now think about commuting conversions, and that makes it much harder to work with these normal forms. So going to a box, an unbox system, is not only practically motivated because it corresponds to box box or quote and splice. It's also motivated because it's actually easier to define normal forms. The trade-off, however, is that you work with some kind of context stack or some kind of lock and unlock mechanism in your context, and you have to deal with these modal weakening and fusion properties. And establishing modal fusion, where you have dependencies among contexts, where you want to lift some of the restrictions that are present at the moment, is really non-trivial. It's really hard. I would also say that the operational semantics is much harder to understand because you have to sort of think about what gets executed at what stage. So that's sort of the trade-off between these two formulations. Now, it is true that you can translate, between them. So, in fact, the original work by Frank and Rowan did not give an operational semantics for box and unbox. Okay, they just translated everything in the box and unbox back to the box let box system, and that's how it was executed. And we have extended their translation between box let box and box unbox also to the contextual type setting. So it scales. All right, so last, to sum up, I think there's sort of a couple of lessons I want to share. I think one important lesson is to sort of see that contextual types internalize sort of our typing judgment and allow us to reason about open terms or partial information or open code in various forms, and this comes up in various settings. Now, the second lesson is that when we talk about open objects, we don't want to commit to a concrete representation of variables. We don't want to think about these variables as the Brin indices. Okay? We want to think about them abstractly and not commit to a concrete representation of these variable bindings or contexts. And so contextual types give you that level of abstraction. Right? Because we unbox an open code with a substitution. The substitution can do the renaming for you, can do the exchange, can do an actual instantiation, can do a weakening. So we can actually work with names and everything remains still sane and alpha renaming holds. And the third lesson, I think, is that contextual types can be considered as extensions to many type systems. It's not something that only makes sense in the simply typed setting. I think it makes a lot of sense when we have polymorphism and also when we have some form of dependent types. But I think having a full dependent type theory, which is multi-staged, okay, not only two stages, but multi-staged, that is still sort of open. But having that would be great because it would really give us a foundation for representing open proofs in systems like Coq or ACTA. It would allow us to write tactics within Coq itself. So this whole idea of writing Coq in Coq or ACTA in ACTA, that would sort of be possible if one has this very strong extension to a full dependent type theory. And that's certainly something I see on the horizon, but it's not something where we're there. So yeah, so last but not least, contextual types have, I think, many applications. They play a big role in incremental program and proof developments. Another work I want to mention is the program development environment Hazelnut, which has also this idea of contextual types to describe sort of these incremental program stages. We've used it in mechanizing meta theory in various forms, and I think it gives also a very good conceptual framework to think about a mechanizing meta theory. And I think it plays also a very important role in multi-stage meta-programming and code generation. So thank you. That's where I'm leaving it at. And I hope you'll get a chance to check out some of this work. And hopefully I've piqued your interest.
Okay, thank you, Brigitte. That's a wonderful talk. I would like to invite questions if there are any from the audience. You could also post it on the Slack channel, or you could raise your hand and then.
Can I see the questions too? Right now, I'll let you handle the question or direct me.
Hi, may I ask? I can't raise my hand because I'm a co-host.
Okay.
May I ask?
Yeah.
So,
You could
yeah,
identify yourself and then ask.
I'm Naoki Kobayashi.
Oh, yeah,
You
sure.
are?
Yeah.
Yeah. So, you mentioned 3 kinds of applications, so listed here.
Mhm.
So, are there any relationship between these applications, or are these very different kinds of applications?
They're really different kinds of applications, and this is an excellent question. Yeah, they're really different applications. So mechanizing meta theory does not have when you look at it, it doesn't have much to do with code generation, but I think there's a lot of cross-fertilization that can happen between them. And the same thing with like incremental program and proof development. It's not something you would immediately connect with mechanizing meta theory or code generation. So in the beginning of 2000 or end of the 90s, there was a lot of work, for example, on trying to describe holes in proofs. And so people were trying to understand how one can do that, and they came up with various systems which had capture allowing substitutions to plug in some things for the whole, and so on. And so I think contextual types sort of provide a different way of looking at this problem. But it turns out that it's really something very general. And when you do mechanizing meta theory, it's a very different scenario where you end up again with needing to characterize a term in a context, because there you're having a derivation tree and you're encountering this derivation tree. You might want to write a program, for example, that counts, even if you just want to do simple program transformations, like counting constructors in your program. Then you will encounter the fact that you will go under a subterm that has a free variable. And the same thing arises when you traverse derivation trees. It's just that these derivation trees are dependently typed. So these are really 3 different applications. So I think it's something very general, a general phenomenon. And I think the fact that it's rediscovered, in the setting of homotopy type theory, in terms of crisp type theory, it speaks to the fact that it is something very general. It's something one should investigate as a general concept rather than just consider it as one thing that is necessary in that particular application.
Okay, thanks.
Okay, so Brigitte, if you mentioned in one of your slides, I think it was slide 17 maybe,
Okay.
About the administrative
Redices.
releases. Yeah.
So this is
So
Redux.
yeah. Uh, so I mean, in the systems that you have worked on, like Beluga and so on, is this taken care of somehow? I mean, is this kind of
Yeah, so because of the fact that R, the result here, right, when you get this open term, which depends on V, this substitution, which plugs in tail of V for this V, is eliminated eager at substitution time. But this Redux cannot reduce, because it's sitting under another function. And we typically don't reduce under functions in function programming languages. It would not reduce at that time. So having a notion of a closure that immediately reduces not only generates better code, but it also simplifies the equational theory you have associated with contextual types. So let me show you the very first example, because I think it's sort of in here. Okay, so when I plug in, when I would say, unify this term with something that has app f and successor of x in it, then I want this h to be immediately equal to app f successor of x, so my term is equal to the result I want it to. I don't want to have an equality theory where I say, oh, what I plug in here will be equal modulo some reductions, okay, because this would be a function. So having this notion of substitutions that come with these open terms, where you gives you, where you already have the reduction applied, right? It's sort of applying the reduction already up front, gives you a much simpler equational theory. And so that's another reason why you want to distinguish between function applications, which are very strong, and sort of this notion of a closure, which already has the substitution sitting there as part of the definition. And so the example you were pointing at, which was here, right? Here we have this function which will, in fact, will not even reduce, because in a functional setting we don't reduce under functions. So to know that this will result in the same term as this term is not obvious, right? It's not just syntax equality. Yeah. It is equality modulo the reduction. And so in many applications, it's useful to think of this open term together with a substitution because it simplifies the equational theory. So that's exactly our original motivation, actually, when we were talking about unification. That's where this also comes up. You have a whole and you want to describe this unification variable. If you describe the unification variable as a closure, then any proofs about this unification algorithm become simpler, because in the end you prove that once you have the instantiation for this unification variable, you have something that is equal, syntactically equal to the result you desired.
Yeah. Thank you. Yeah. Are there other questions? We could.
I think Ugo.
Yeah.
I see Ugo raising his hand.
Yeah.
May I?
Yeah.
Yeah. So first of all, thank you very much, Brigitte, for the wonderful tutorial. So during the tutorial, I was wondering about the following, maybe because I'm working on the subject. So I was wondering whether contextual type theory could handle calculi in which maybe part of the context is treated linearly and part of the context is treated non-linearly, in the sense of, if you know it, Benton's linear non-linear stuff. And I was wondering about it because some of these calculi are used, for example, in quantum computation, in which you have like some part of the calculus dealing with circuits and a part of the calculus dealing with generation of circuits. And so in these cases, I guess that working contextually would be interesting, would be extremely interesting. And so I was wondering about it. Can you comment?
Yeah, that's a great question. So so in general, you can certainly strip this up as a linear system. There's nothing which restricts it to being just an intuitionistic context. It just means you have different properties, for example, for substitution, what kind of substitutions you would allow. And in fact, we had a paper at ESOP where we describe LICS, which stands for linear contextual type theory, which has a linear context. So it doesn't mix linear and non-linear, but I think you could also mix them. Then you would have just the two contexts there. But in this work, which we called LICS, it's essentially this context here is linear. And one of the complications is, so we wanted to reason about these linear representations of contextual types. So we had abstractions, we abstracted over the free variables that occur. So here it's only one, but in general it could be any. So we have these context variables. And then that means you need to merge or combine two contexts which possibly have two context variables. So there's essentially a monoidal structure on how you combine these contexts together.
I see. Thank you very much.
So Brigitte, there is a question on the Slack channel.
Yeah.
This is from Thomas Yakel. So Thomas says that in Haskell code, generation is done during compile time. Can you somehow distinguish between runtime code and compile time code?
Yeah, so that's another reason of using box and unbox, or box and letbox, in particular in this work by Frank and Rowan. That was exactly the distinction. So one, the generation at runtime was what I called the generation of code, and then the generated code was essentially then done at compiled. Well, that's sort of what you would consider compiled code, and you would run it separately. So this is often associated with this multi-staged programming setting. That's indeed the same kind of view. Yeah, it's compatible.
Excuse me, Supratik, you are muted.
Oh, I'm sorry. Yeah. Are there any further questions? If not, I guess we've also reached the end of the slot. So let me thank Brigitte again for a wonderful talk. Very nice. It sort of made things clear even for those who are not experts in type theory. So thank you, Brigitte, again for that enlightening talk. And I guess that closes this session, and then there's a coffee break, I believe, Holger.
We are at the end of the day. At least in Europe, it's approaching end of day. Not in everywhere on this globe.
Okay. So
thanks a lot.
Yeah, thank you.
Thank you, everybody. Thanks, Brigitte.
Thank you.
Thanks everybody for coming to the session. So Florian, it's up to you now. The controls of the session.
Yes.
Yeah, I just want to mention that the Slack channel, you could post your comments. All right, so I guess we leave the session. Florian, is that correct? It's the end of the time slot.
We can leave it open if you need it. I would stop the live stream now.
Okay.